Thanks for the introduction. So if you are attending this session, you probably know that it's important to protect secrets against microarchitectural side channel. So to do this, cryptographic libraries usually use a countermeasure called constant time programming. And basically the idea is that you will write your code in such a way that secrets do not flow to insecure instructions. And by insecure instructions, I mean instructions that can leak their operands via timing or to the microarchitecture. And here, I mean the cache or branch predictor, pick your favorite microarchitectural side channel. So for instance, here we have a code that is constant time because they reference an array with an index that can be provided by the attacker, but before that we check that the address is in bound. And then we leak the resulting value to the microarchitecture, but only public data in this code can leak. We never access the secret. So you might think our program is constant time, it is secure, but you might know that it's not that easy because of speculative execution. So what happened actually when the CPU executes this program is that when the condition here is about to be executed, if, for instance, for some reason, the condition is slow to resolve because length is not in the cache, the processor, instead of stalling, waiting for the value, will start executing, we'll try to predict the condition and will start executing. So in this example, if we predict that the branch is taken with index out of bound, we will, at the second line, load the secret, and at the third line, leak the secret to the microarchitecture. This leakage this secret to the microarchitecture is not reverted. So once we leak the secret in transient execution, it's there for the attacker to be observed. And this is this is Spectre attacks. So now we know that constant time code is not enough to protect against Spectre. How do we do to protect against these attacks? A solution is to use, to change our programming models and to use speculative constant time. So in essence, we would have to, as a developer, reason about all the way processors can use speculative execution and place mitigations accordingly. Unfortunately, it's a bit hard to do that because there are multiple sources of speculation in processors. And if tomorrow hardware designer come up with new speculative execution mechanisms, it means that we have to fix our programming models and to fix our software. So we definitely don't want to do that. Instead, I think that developers shouldn't care about speculative execution. And instead, the hardware should make sure that in speculative execution, secrets are not leaked. But of course, we don't want to just disable speculation because that would be awful for performance. And what would be nice to have is a hardware defense that still provides speculation, but that protects secrets from leaking during speculative execution. And so I call this secure speculation for constant time. It turns out that there are actually there is actually a class of hardware defenses that are a good candidate for this. And they all implement what I will call hardware secrecy tracking. So in essence, on the software side, we will label the secrets, like for instance, by annotating them in the source code, and make sure that the program is constant time. And on the hardware side, we will track the secrecy, track the secrets soundly during computations, and we will make sure that if we're in speculative execution and operating on secrets, then we don't make the secret flow to insecure instructions. And otherwise, we just block speculative execution and wait for it to be resolved. So there are already a couple of papers that describe this mechanism, but there is still a question. How do we know that these defenses work? How do we know that they actually provide secure speculation for constant time? And that's what we answer in our paper. And to do that, we use the hardware-software contract that was proposed a couple of years ago, and we adapted to account for more speculative execution mechanisms, because it was only proposed for, well, Spectre v1, and we want to cover all variants of Spectre, but also LVI. We might also want to account for futuristic speculation mechanisms like value prediction and load value prediction. And we also need to adapt it for declassification. And finally, there is another challenge, which is that all the previous work I mentioned, they don't provide synthesizable implementation, so they cannot evaluate hardware costs. So in our paper, we propose ProSpeCT, a formal processor model that implements hardware secrecy tracking. And we prove that it enables secure speculation for constant time programs. It allows for declassification, and it is generic in the sense that it covers all Spectre variants plus LVI. We also consider load value speculation. And when doing the proof, we realized an interesting thing is that sometimes we need to roll back correct speculations to preserve security. I won't have time to talk about it today, but you can check the paper if you're interested. And finally, we implemented the defense in a RISC-V microarchitecture. So let me illustrate quickly how this works. So here we have again our example that was vulnerable to Spectre v1. And so with ProSpeCT, as a developer, I will first have to label the memory, the secret in the memory. Then the processor might still enter speculative execution on the condition here. But when the secret is loaded when the secret is loaded, we will propagate a label. We will attach a label to the value, and because we're on the third instruction, because we're in speculative execution and we're operating on a secret, we won't forward X to the insecure instruction. So the idea is pretty simple. Of course, there are some more details in the paper, but at least you get the gist here. And so we formalize this defense in the semantics of an out-of-order speculative processor. And in this semantic, we leak every public data to the attacker, meaning that, the attacker can observe all public data, but also predictions can depend on any public value, and that allows us to express a lot of different speculative execution mechanisms. To declassify data, to declassify secrets, we just have to write them to public memory. But that also means that we, as a programmer, need to make sure that we don't unintentionally declassify secrets. And finally, we prove that if a program is constant time, meaning if it doesn't leak in an in-order semantics, then on this hardware with a speculative out-of-order semantics, it will not leak. So we then implemented this defense on top of a modular RISC-V processor called Proteus, which is designed to be easily extensible. It comes with speculation because it has branch target prediction, and it's the processor and the defense are on GitHub, so I encourage you to check it out. And we evaluate the hardware cost of the defense, which is quite acceptable and can probably also be reduced with more engineering effort. And finally, we evaluate the annotation burden and the performance overhead. So for the annotation burden, we took 4 primitives from ACOSTAR. We annotate all the secrets. We make sure that no secrets are declassified unintentionally by being written to the public stack. And just manually, we were able to do that in 3 out of 4 cases. And I think this can be very easily automated by a compiler. And it was not that hard. It took less than an hour per primitive. For the performance, we see that there is no overhead for constant time code when the secrets are precisely annotated. And if you think about it, this is quite neat and a bit expected, because when we block a speculation, it's only when there is a secret flowing to an insecure instruction, which actually should never happen in cryptographic code, well, in constant time code. And that means that we are only blocking mispredicted instructions. So to conclude, I presented a hardware-software co-design where the software informs the hardware about secrets, and the hardware used that information to provide strong security guarantees with a low overhead. And I really think that this is this is a good compromise between security and performance.